Hello, welcome to the second lecture in this series. So we were discussing the Hermet's differential equation and Hermet's polynomial. So first of all, Hermet's differential equation is y double prime minus 2xy prime plus 2 lambda y equal to 0, where lambda is a parameter, where lambda is a real parameter, and it's a second order ODE, which is variable coefficient ODE. Okay, so now we can do the following. We can solve this ODE y double prime minus 2xy prime plus 2 lambda y equal to 0 using power series method. That is a very easy thing to do. All of you can do this power series substitution and try to find a power series solution of this equation. Now, if you do the power series solution of this equation, you will realize that when lambda is equal to 0, 1, 2, 3, etc., one of the power series terminates, and that gives you a polynomial solution. And that polynomial solution, that polynomial has degree exactly equal to this lambda. When lambda equal to 0, 1, 2, 3, etc. So for example, when lambda is 36, then you get a polynomial solution of degree 36 exactly. And that polynomial is called the Hermet's polynomial. That polynomial is called the Hermet's polynomial. What we do is that we substitute y equal to u e to the power x squared by 2 into the differential equation, or u equal to y e to the power minus x squared by 2. So just make the substitution and find the differential equation for u prime. The differential equation for u is u double prime minus x squared u plus 2 lambda plus 1 u equal to 0. Now, what is the advantage of this substitution? So since we know that if lambda is 0, 1, 2, 3, dot, 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 we know that there is a polynomial solution. Suppose if lambda is 36, then we know that there's a polynomial solution of degree, with polynomial of degree 36, which satisfies this differential equation. So take that polynomial, take that Hermet polynomial of degree 36 and multiply by e to the power minus x squared by 2. You get a u. This u is in the Schwarz class, and this u satisfies this differential equation, u double prime minus x squared u plus 2 lambda plus 1 equal to 0. So that becomes so now look at this operator, u double prime minus x squared u. Look at this operator, u double prime minus x squared u. And that is equal to minus 2 lambda plus 1 u. So you know that if you take the Hermet polynomial and multiply by e to the power minus x squared by 2, you get a Hermet function, and that Hermet function is an eigenfunction for this operator u double prime minus x squared u. Because when you apply to u double prime minus x squared u, you get a multiple of u. So you get an eigenfunction. But what is the speciality of this u double prime minus x squared u? Or you can think of it as minus u double prime plus x squared u. You can change sign throughout the differential equation, not a problem. What is the advantage of that differential equation? That differential equation, when you take the Fourier transform of minus u double prime, you are going to get chi squared u hat. When you take the Fourier transform of minus x squared u, you are going to get minus the second derivative of the Fourier transform. So this part, u double prime minus x squared u, when you take the Fourier transform, you get the same expression with a negative sign. So this differential equation that you see, the differential equation for u is invariant under Fourier transform. That's what the second exercise says. And for the transformed ODE, for the u equation, hnx into e to the power minus x squared by 2 is a solution. And this solution lies in the Schwarz class. And hn is the nth Hermet polynomial. That is, when you take lambda equal to n in the y equation, you get a polynomial solution. That polynomial solution is hn of x. Okay, so that is there are some of the exercises, and the significance of this you will see in connection with quantum mechanics. You can look at perspectives of modern physics by Arthur Beiser. Now we have seen that the Fourier transform is a linear transformation from S to itself. The linear transformation from S to itself. And the function can be recovered from the Fourier transform by what is called as the inversion theorem. So let f of t be a function in the Schwarz class, and we have the Fourier transform f hat of chi. If I give you the Fourier transform f hat of chi, then I can get my original function back. How do I get it? Equation number 6 in the display. F of t equal to 1 upon 2 pi integral minus infinity to infinity f hat chi e to the power I t chi. Look at the sign plus here. In the definition of the Fourier transform, we had a minus sign. Here we have the plus sign. Please make a note of this. If you put a minus here, that's wrong. It's important that the sign here is plus. And there's a factor of 1 upon 2 pi. So now we have to prove this important theorem called the inversion theorem. So as an immediate application of the inversion theorem, suppose the Fourier transform is 0. Suppose f hat is 0. Then the inversion theorem tells you that then f has to be 0. So the Fourier transform is 1, 1. The Fourier transform is injective. It also tells you that the Fourier transform is surjective because you can use this same equation 6 to prove that the Fourier transform is surjective. Suppose you're given a function f in the Schwarz class. Then I want to show that this f is a Fourier transform of something else. As a first guess, f is already in the Schwarz class. So f hat is in the Schwarz class. So I try whether f hat will recover the function. It doesn't. Why doesn't it recover the function? Because of the sign change. It is f hat, then I have to take f hat hat. F hat hat, you'll have to try f hat hat and make a small modification and you will get it. So you can use the same formula 6 to show that the Fourier transform is surjective, right? I'll tell you a very simple way to do this. In this integral 6, I make a change of variables, chi going to minus chi. Make the change of variables, chi going to minus chi. Then what happens? The Jacobian is 1, and then it becomes e to the power minus it chi, and you get f hat of minus chi. So which function? Suppose I give you a function f of t in the Schwarz space, then f of t is a Fourier transform of what? It is a Fourier transform of f hat of minus chi with the appropriate with multiplied by 2 pi. So f is a Fourier transform of 2 pi times f hat of minus chi. That's what equation 6 tells you. That we see that the Fourier transform is also surjective. So Fourier transform is a bijective linear transformation from S to itself. This is the most important conclusion from the Fourier inversion theorem. All right. So now we have to prove the Fourier inversion theorem. So let us do the obvious thing. Let us now take this integral and let us try to prove that RHS equal to LHS. So the idea is try to prove that RHS equal to LHS. So we start from RHS. And you put the definition of f hat of chi. What is the definition of f hat of chi? Integral minus infinity to infinity f of t or f of s you can take. Because the t is already present, you take some other variable for the integration. F of s e to the power minus I s chi ds. That's what you will do. And then the obvious thing that you will do will be, you get two integrals. You get a repeated integral, right? And you want to exchange the order of integration. You should do that. So you should put the definition of f hat. What is f hat of chi? Again, integral minus infinity to infinity f of x. I take an f of x e to the power minus I x chi dx. So inner integral is dx, the outer integral is d chi. Switch the order of integration. The outer integral will be dx and the inner integral will be d chi. So outer integral will involve integral minus infinity to infinity f of x dx. And what is the inner integral? Inner integral will be e to the power I t chi minus I x chi. X of I chi into t minus x d chi. This is a display. This is what you see in the displayed slide. There's one small problem with this, right? And what is that small problem? This integral doesn't converge. What is the meaning of this integral? Well, how do you define this integral? This doesn't, not a convergent integral. So you're now run into the oscillatory integral or hitherto meaningless integral. So what you do to cope with this, you got to correct it. You got to modify this strategy. This strategy won't work. So let us see how to modify this strategy. Now let us again start with the right hand side. Let me forget about this 2 pi factor for the time being. Start with the right hand side of 6, right? This is the right hand side of equation 6. Okay. Integral minus infinity to infinity f hat chi e to the power I t chi d chi. Let us write it as limit as epsilon goes to 0. Integral minus infinity to infinity f hat chi e to the power minus I t chi into e to the power minus epsilon chi squared. I had thrown in an e to the power minus epsilon chi squared inside the integral because as epsilon goes to 0, e to the power minus epsilon chi squared goes to 1. Okay. So now let us keep this limit as epsilon tends to infinity, epsilon tends to 0 outside, integral minus infinity to infinity. And now let us put in the definition of f hat of chi. The definition of f hat of chi is integral minus infinity to infinity f of x e to the power minus I chi x dx. We put that. Now we can switch the order of integration. What we tried earlier which didn't work, let us try whether it works now. I'm going to say it's going to work now because its limit as epsilon goes to 0, integral minus infinity to infinity. Then I switch the order of integration. The d chi integral goes first and the dx integral goes last. So fx dx. What is the d chi integral? Integral minus infinity to infinity e to the power I chi t minus x minus epsilon chi squared d chi. The inner integral is a Fourier transform of the Gaussian, right? You see what you have here. You got the e to the power minus epsilon chi squared. And then you're taking the Fourier transform, e to the power minus I chi x minus t. You can t minus x can be made into x minus t with a minus sign. So you see exactly, you recognize the Fourier transform of the Gaussian. But you know that the Fourier transform of the Gaussian is another Gaussian. So what is it going to be? Remember, there's a minus epsilon chi squared. So it will be root pi by epsilon. If you go back to the formula for the Fourier transform of the Gaussian that we have done in the earlier lecture, you get root pi by epsilon. You're going to get limit as epsilon goes to 0 is still outside. You're going to get integral minus infinity to infinity x of minus x minus t the whole squared upon 4 epsilon fx dx. Now we want to make this exponential factor easy. So let us put x equal to t plus root 4 epsilon s. This square root is only for 4 epsilon, not for s, by the way. So what do you get? Dx equal to what? Dx equal to root 4 epsilon ds. So the root epsilon cancels out and root 4 is 2. And so you're left with 2 root pi limit as epsilon goes to 0. And then x has been put what? X minus t is root 4 epsilon. So the 4 epsilon cancels out. You simply get e to the power minus s squared ds f of t plus root 4 epsilon s. And take the limit as epsilon goes to 0 inside the integral. And as epsilon goes to 0, this root 4 epsilon s goes away. You simply get f of t. This f of t comes out because in integrating with respect to s, you get e to the power minus s squared ds is again root pi. So root pi, you get pi, you get 2 pi f of t, and the proof is complete. So this is a very beautiful application. This is a very beautiful illustration. Two things are illustrated. We have proved the inversion theorem completely. And second thing we have done is that we have introduced a new idea called the e to the power minus epsilon t squared trick. Now this e to the power minus epsilon t squared trick, which was used here to prove the inversion formula, can also be used for a variety of other situations. And there are a number of exercises for how to use the e to the power minus epsilon x squared trick. Try to prove this result. Integral minus infinity to infinity f hat chi d chi is 2 pi f of 0. If you try to directly write the definition of the Fourier transform and switch the order of integration, you're going to get into the same trouble. So introduce the e to the power minus epsilon chi squared and then do the job. Try to calculate the Fourier transform of sine at by t. So these problems can be done using the e to the power minus epsilon epsilon chi-squared trick. Okay. All right. There are a number of other problems, but here let us now focus on one problem on the e to the power epsilon x squared trick, which I personally want to bring to your attention. Now we are going to see a beautiful formula of Ramanujan. I hope everybody has seen the movie of Ramanujan, The Man Who Knew Infinity. If you haven't seen the movie, I urge you to watch that movie. It's a great movie. It's a great tribute to this great man, Ramanujan, Srinivasan Ramanujan. So Srinivasan Ramanujan, as you know, has given large number of very beautiful mathematical formulas, and these Ramanujan's formulas have all been compiled in his notebooks, 3 notebooks. These notebooks have been edited by Bruce Burnt and others, and now they are available. And now if you open up these Ramanujan's notebooks and you just flip through it, you will realize that the gamma function featured prominently in several formulas of Ramanujan, numerous ones. And right at the beginning, I mentioned that there is a very nice example of a Schwarz function. What is it? Take a positive real number, gamma a plus it. Gamma a plus it, take mod squared. That's an element of the Schwarz space. And so if it is an element of the Schwarz space, then I'm curious to know what is the Fourier transform. What is the Fourier transform of this? In other words, I have to compute integral minus infinity to infinity mod gamma a plus it squared e to the power minus it chi dt. I want to calculate this integral explicitly. It turns out that the integral can be calculated explicitly. Root by gamma a plus half sech squared. Sech is reciprocal of cosh. 1 upon cosh is sech. Hyperbolic secant to the power minus 2a chi by 2. This explicit formula for the Fourier transform of the mod of the gamma function along vertical lines in the right half plane was obtained by Ramanujan. Now Ramanujan's proof was quite tricky. I mean, Ramanujan was a genius, and he was a wizard when it comes to manipulating formulas. His proof is quite tricky, and but I was able to give an alternate proof using the e to the power minus epsilon x squared trick, and you will find the relevant argument in our joint paper, Devraj Chakravarti and G.K. Srinivasan, on a remarkable formula of Ramanujan which appeared in Archive der Mathematik about 9 years ago. So that is the another application of the e to the power minus epsilon squared trick. All right, so now let us skip these slides a little bit and let us go a little further. Okay, so another application of the Gaussian Fourier transform of the Gaussian, but let's just skip, we don't have time for this. Now let's go to the next item in this series called the Parseval Formula. Sometimes it's also known as the Plancherel's theorem. Plancherel's theorem or Parseval's Formula. So what does the theorem say? The theorem has been stated as theorem number 45 in these slides. Suppose f of t and g of t are both in the Schwarz space, because they're both rapidly decreasing, and you look at integral minus infinity to infinity f of t gt bar dt, then it is the same as integral minus infinity to infinity f hat chi g hat chi bar d chi, with the 1 upon 2 pi thrown in. Equation number 7 on the slide. One can prove this, again, one can sit down and prove this, RHS equal to LHS. How do you do RHS equal to LHS? Write down the Fourier transform of f, write down the Fourier transform of g. You will get a triple integral, you will get 3 integrals because already there's an integral with respect to chi. And then you have to switch the order of the integration. Again, you will run into the same problem that we encountered when we did the inversion formula. So what is a way out? No prizes for guessing. You have to use the e to the power minus epsilon t squared trick. Okay, so you can use that and you can prove the formula. So since the arguments are repetitive, I won't give the detailed argument. I'll just leave it to you to prove it. The next thing is the notion of convolution. What is a convolution of two functions ft and gt? Now let me recall for you the definition of convolution. Now you have studied convolutions maybe in connection with Laplace transforms. If you don't know what is a convolution, hear me out carefully with a piece of paper. Please jot down what I'm going to write very, very clearly. F of t and g of t are both functions defined on the real line. Okay, we are defined, f and g are defined on the real line. That's the first thing. The domain should be a group, should be an abelian group. And in this case, the abelian group is real numbers under addition. Okay. So if you're given two functions f and g on the real line, say they are both integrable functions, mod f and mod g are both integrable. What is f star g? F star g of t. Please hear me out clearly and please write it on a piece of paper because we will need this definition when we try to prove equation number 8. What is f star g of t? F star g of t equal to integral from minus infinity to plus infinity f of t into g of x minus t dt. F star g of x, I repeat, f star g of x equals, f star g of x equals integral from minus infinity to infinity f of t g of x minus t dt. Exercise, check that f star g equal to g star f. Check that f star g equal to g star f. The convolution is commutative. Now, what does the Fourier transform do? Now, first of all, you have to check that if f and g are both in the Schwarz space, then the convolution is also in the Schwarz space. Now, we will not do this theorem. We will just take it for granted. The convolution is also in the Schwarz class. So, what is the Fourier transform of the convolution? Very beautiful formula. The Fourier transform of f star g is a Fourier transform of f into Fourier transform of g. The Fourier transform converts the convolution product into a simple product. Okay. So let us now use this. The proof is very easy. One can use the inversion theorem to do it. A verification of this is an easy exercise. You simply have to compute left LHS equal to integral f star g x into e to the power minus ix chi dx. But what is f star g of x? You put in the definition I just gave you, switch the order of integration, and there you are. That's it. There's nothing much to be done. So it's a very easy exercise and I'm leaving it to you to complete the job. Let us look at the application of this convolution. This is called the convolution theorem. Let us look at an application of the convolution theorem. Let us solve the heat equation. So let us look at the heat equation. What is the heat equation? The heat equation is a partial differential equation ut minus uxx equal to 0. So it's an evolution equation. So at t should be thought of as time and x should be thought of as space. It's a one-dimensional heat equation. Okay, and the heat distribution, the temperature distribution at time t equal to 0 is given to you, and that is given to you as f of x. U of x comma 0 is f of x. Let us assume that this is called the initial value or the Cauchy data. This initial value, initial heat distribution f of x is assumed to be in the Schwarz space. F of x is assumed to be in the Schwarz space. And now let us compute the Fourier transform. Let us think of u. So u is a function of two variables, u of x comma t. U of x comma t. Now I'm going to think of t as a parameter and I'm going to think of x as the active variable for the Fourier transform, for purpose of Fourier transform. So I'm going to assume that the initial heat distribution is also in the Schwarz class, and I'm also going to assume that I'm going to take the Fourier transform with respect to the x variable. So when I'm computing the Fourier transform of the x variable ut, what is the Fourier transform of ut? It is ddt of Fourier transform u hat of chi t. And the second one, minus uxx. What is the Fourier transform of minus uxx? Remember the rules, momentum and position get exchanged. 1 upon id dx and multiplication by x get exchanged and it becomes chi squared u hat. So minus uxx become chi squared u hat. And of course, so you Fourier transform the initial data also. U hat of chi comma 0 will be equal to f hat of chi. Well, you get a familiar ODE. It's like y double prime plus chi squared y equal to 0. You know how to solve, sorry, y prime plus chi squared y equal to 0. It's a first order ODE. So it's a first order linear ODE. Very nice. You can solve it directly and you can get u hat of chi t. You have u hat of chi t is constant times x puff minus t chi squared. Straight away you can solve this first order linear ODE. And of course this constant is a constant of integration and you have to find the value of the constant of integration. You put t equal to 0. Put t equal to 0 and you immediately get that c equal to u hat of chi comma 0. U hat of chi comma 0 is f hat of chi. So you got the answer u hat of chi comma t equal to f hat of chi into e to the power minus t chi squared. Now can you write this e to the power minus t chi squared? That's a Gaussian, right? E to the power minus t chi squared is a Gaussian. You know that the Gaussian is a Fourier transform of some other Gaussian. If you take the Gaussian and take its Fourier transform, you get another Gaussian. So this e to the power minus t chi squared can be written as the Fourier transform of some other object. Let us call that other this g. So this e to the power minus t chi squared is, say, the Fourier transform of capital G. So let us call it G, capital G hat. So u hat becomes f hat into capital G hat. But f hat into capital G hat is what? By the convolution theorem, it is G star f the whole hat. So you get u hat equal to G star f the whole hat, or you get u equal to G star f. And you solve the differential equation. You solve the heat equation and the job is complete. Right? So let us solve the heat equation. So we came up to the point where u hat chi t equal to f hat of chi exponential of minus t chi squared, and we know that exponential of minus t chi squared is a Fourier transform of 1 upon root 4 pi t exponential of minus x squared by 4t. So putting this in, we get that u hat of chi t equal to f hat into g hat, where this g is this function. This function is called the heat kernel. And so by convolution theorem, this product is g star f the whole thing hat. So thus we have u of xt is going to be equal, taking the inverse, since the Fourier transform is injective, u of xt equal to 1 upon root 4 pi t integral minus infinity to infinity f of s exponential of minus x minus s squared upon 4t ds. So we have obtained a formula for the solution of the heat equation with initial conditions. This heat kernel plays an important role in probability theory. The formula was derived assuming that the initial data f of x is in the Schwarz space. Now the integral, for example, if you look at equation 9, the integral makes perfect sense even if f of s is not in the Schwarz class. For example, if f of s is just a bounded function, for instance, any bounded function, it will still work. Say bounded continuous function you take, or even with finite limited discontinuities, doesn't matter. Integral will make perfect sense. And you can keep differentiating under the integral sign as many times as you want, because this exponential factor is present to help you. And it will satisfy the heat equation. So we can directly check. So actually the same heat equation can be solved with f of s which is not in the Schwarz class. So here are some examples. So for example, I could take f of x equal to x squared. So you put s squared and you compute this integral and you get the solution of the heat equation. The next exercise, you are asked to solve the heat equation with initial condition u of x0 equal to cos ax and sin ax. So put the thing over here, f of s equal to cos as, and compute this integral. You'll have to again use the formula for the Fourier transform of the Gaussian. put x minus s equal to u, and then expand this cos using the addition formula for cosine. Now suppose, for example, I give you the initial condition, which is a continuous function. So I take an initial condition which is continuous function, which is positive on the minus 1 1 and 0 outside minus 1 1. So inside open interval minus 1 it's positive, and outside the closed interval minus 1 1 it is 0. Then let us look at this. Let us look at this solution. What will happen to the solution? F of s is 0 outside minus 1. So integral will go from minus 1 to 1. And f of s is positive between minus 1 and 1. The exponential factor, of course, is positive. So u of xt, no matter what the value, so u of xt is going to be positive for any positive t. The moment t becomes bigger than 0, say 1 upon root 4 pi t is positive, you're integrating from minus 1 to 1, something that is positive. You're going to get a positive value. No matter where your x is, your x could be very, very far away and t could be very, very small, and immediately the integral 9 coughs out a positive value, right? Integral coughs out a positive value. Now let us think in physical terms. The function f of s, the initial temperature distribution, think of an infinitely long rod, and the rod, the initial temperature distribution, say between minus 1 and 1 is positive, and the temperature distribution outside minus 1 1 is 0. That is the initial temperature distribution. Now moment time becomes positive, say within a few nanoseconds, and x can be very, very far, say x could be 10 kilometers away. So what it is saying is that if you take a point in the rod which is 10 kilometers away, and within a few nanoseconds, even if you take time to be in the order of nanosecond, the initial temperature distribution from minus 1 to 1 would be felt. The temperature, that will be positive temperature, even if x is 10 kilometers away and t is just 1 nanosecond. How is it possible physically that when the rod is heated from minus 1 to 1, then instantaneously the heat propagates, say 10 kilometers away or even beyond? So this is expressed by this, what is written in red. The effect of initial heat distribution in minus 1 1 is instantaneously propagated throughout space. The question is this physically tenable? Obviously it's not physically tenable. But how is it that this equation, nevertheless, if it is not physically tenable, then how is it that the heat equation is used to explain physical phenomena? The point is, although u of xt is positive when x is very far and t is very, very small, the value of u is really, really small. And so it is well within the tolerance of experimental errors and stuff like that. After all, when we are modeling a physical situation, and while making this model, we are going to make simplifying assumptions. And these simplifying assumptions are going to cause a slight deviation from reality. So this is not a problem. This is to be expected. Now this Jacobi theta function identity, I will leave it. Now we will go to the next topic, the D'Alembert's solution of the wave equation. So at the beginning of this chapter, we were looking for solutions of the wave equation, utt minus uxx equal to 0. And we obtained the solution in the form phi of x plus t plus psi of x minus t. Remember, right at the beginning we saw this two integrals, one of them involved in x plus t, the other one involved in x minus t. So now let us supplement this with initial conditions. The u of x comma 0 equal to f of x, ut of x comma 0 equal to g of x. It is second order in time. Again, t should be regarded as time and x should be regarded as space. And it comes from Newtonian dynamics, and so two initial conditions are to be given: the initial displacement and the initial velocity. And let us see. Let us put t equal to 0 in the equation. We'll get phi of x plus psi of x equal to fx, and then differentiate this equation u of x t equal to phi of x plus t plus psi of x minus t, and then put t equal to 0. We get phi prime x minus psi prime x equal to gx, and then we get phi prime of s equal to f prime of s plus g of s, and psi prime of s equal to 1/2 of f prime of s minus g of s. We immediately get the formula for the integrate phi and psi and put it here. And we immediately get the formula u of xt equal to 1/2 f of x plus t plus f of x minus t plus 1/2 integral gs ds from x minus t to x plus t. This is known as the D'Alembert's formula for the wave equation. So now using the D'Alembert's formula, you can solve the wave equation for a variety of initial conditions. I've given you the next few exercises deal with that. So solve the wave equation utt minus uxx equal to 0 with initial conditions u of x comma 0 equal to 0, ut of x comma 0 equal to 1 minus x. You simply have to take f of x to be x and g of x to be 1 minus x and compute these integrals that appear in equation 10, and the job is done. Ditto for the next problem, where the initial conditions are sin x and ut is 0. Ut is 0, so g is 0, so straight away the second piece is 0, integral piece is 0. The first one is sin of x plus t plus sin of x minus t, and we can just compute that. Now, suppose V1 is a solution of the wave equation, utt minus uxx equal to 0, and V2 is a solution of the solution with data of the first solution altered along 2, 3. What happens is that you are taken a solution of the wave equation and you're tampering the data so you're taken one solution, V1, okay? So whatever, some solution, you don't know what that solution is. What I'm saying is that the data is tampered in the interval 2, 3. In the interval 2. So in your txt plane, you plot the x-axis and you plot the t-axis, and then you mark this interval 2, 3. Sketch the region in the xt plane where v1 and v2 will agree, and sketch the regions where v1 and v2 will disagree. Now, you have to stare at this formula 10. Let us look at this formula 10 from a geometrical perspective. What is happening? You take a point x comma t. You take a point x comma t in the upper half plane, for example. Take t positive just for simplicity. And then from the point, take for example 1, 1. Let us take the point 1, 1 just to give you an idea. Then through the point 1, 1, you draw two lines, sloping at an angle of 45 degrees and sloping at an angle of minus 45 degrees. So from 1, 1, you draw the two lines with slopes 1 and minus 1, and they will intersect the x-axis. Where will they intersect x-axis? If you take a point x comma t and say x naught comma t naught, and you draw two lines with slopes plus 1 and minus 1, then they'll intersect the x-axis at the point x naught plus t and x naught minus t. And then you're adding the value of the initial condition at these 2 points and averaging. And then what you're doing is that between the same 2 points, you're integrating the other data g, and then you're putting this factor of half. So that is how, so you know exactly that if you want to calculate the value of the solution at a point x naught, t naught, then to calculate the value, you need the value of f. You draw these two straight lines at which slope 1 and minus 1. See the line segment. See the 2 points where they hit the x-axis. And at those end points, you need the value of f. And for the value of g, you need in the you need the value of g in the points in the interval between x naught plus t and x naught minus t. Now that should tell you that if to calculate the value at a point, now I'm altering the data at 2, 3 in the interval 2 to 3. I'm altering the data. So what you do is that from the point 2, you draw a line with slope -1, and from the point 3 you draw a line with slope 1, and you got this inverted trapezium, infinite trapezium. So take the point 2, 0 on the x-axis and 3, 0 on the x-axis. From 2, 0, line with slope -1, from 3, 0, line with slope +1, and then you draw that entire region. Now if I take a point x0, t0 outside that region, then x0, t0, then from x0, t0, if I draw those two straight lines with slope 1 and -1, then the line segment that it determines on the x-axis will be well outside 2, 3. So altering the data at 2, 3 will not alter the value of the function at x0, t0 if the x0, t0 is outside this inverted trapezium. So for points in the inverted trapezium, the V1 and V2 will definitely disagree, and for points outside the inverted trapezium, V1 and V2 will definitely agree. I'd like you to draw pictures of this and try to convince yourself about the correctness of what I said. This is a very beautiful geometrical way of looking at the one-dimensional wave equation. And the next problem is along similar lines. A, B, C, D are the vertices of a rectangle whose sides have slopes 1 and -1. And if U is a solution of the wave equation, then UA plus UC equal to UB plus U. It will follow immediately from the Lambert's formula. So try these problems out. So now let us come to the next topic, the radial functions. So the Fourier now we have seen time and again that if your function is an even function and you're trying to compute the Fourier transform of an even function, then the sine term disappears, and then e to the power minus I x chi, you'll have a cos x chi. So essentially it is integral from -infinity to infinity f of x cos x chi. What it means is that if the original function is an even function, the Fourier transform is also an even function. If the original function is an odd function, the Fourier transform is also an odd function. But evenness and oddness, the property in one dimension, what is the corresponding property in several dimensions? Multidimensional analog of that. Multidimensional analog of it are radial function. When is a function f? Say, let us take a function of two variables. When is a function f of x1, x2, or when is a function of x and y, f of xy? When would you call it a radial function? So what are examples of radial functions? For example, f of xy equal to x squared plus y squared. That's an example of a radial function. It depends, the value of the function depends only on the distance from the origin. In other words, if I apply a rotation matrix, so if I think of f as a function of x and y, and if I think of x and y as a column vector, think of x and y as a column vector in R2, then f of xy is the same as f of axy, where A is an orthogonal matrix, a 2 by 2 orthogonal matrix. Similarly in 3 dimensions, so f of x1, x2, x3. So think of x1, x2, x3 as a column vector, just to think in matrix language. So f of x1, x2, x3 is said to be radial if f of x1, x2, x3 or f of x equal to f of ax, where A is a 3 by 3 orthogonal matrix. So now you understand the definition of a radial function. A function f of x1, x2, xn, think of x1, x2, xn as a column vector. F of x is said to be radial if f of x equal to f of ax, where A is a n cross n orthogonal matrix. Such a function is a radial. A simplest example of a radial function is x1 squared plus x2 squared plus dot 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 plus xn squared. For example, in R3, you can write a function in polar coordinates. We put x equal to r cos theta sine phi, y equal to r sine theta sine phi, z equal to r cos phi. In the function f of x, y, z depends only on the radial coordinate. If it is some function of psi, if it is a function psi of r, then you will say that the function is a radial function. What we want to understand is that if I take the Fourier transform of a radial function, the result is again a radial function. That is a very important property about the Fourier transform. Another way to talk about it is that the Fourier transform is invariant under rotation of coordinates. The Fourier transform is invariant under rotation of coordinates or the symmetry in the Fourier transform operator. So this is a very important topic, and we shall see that this has some profound implications. When you take the Fourier transform of a radial function in R2 and if you take a Fourier transform of a radial function in R3, the character of the Fourier transform is quite different, and that is what we want to now find out. So let us take now, first of all, before we even embark upon this, we have to define the Fourier transform of a function of several variables. So far we have been talking about Fourier transform of a function from R to C, one variable, function of one variable. What about functions of two variables or three variables? So f of x1, x2, xn is a, say, assumed to be a nice function, continuous function which decays rapidly enough. So again, I can define the Schwarz space of several variables. You can define it exactly as you define the Schwarz space of one variable. Only thing is that over there we differentiated the function n times, but now we have to take all sorts of partial derivatives. We can differentiate, but we can take the derivatives of order n, but involving, so del alpha, so del nu by del x1 to the power alpha 1, del x2 to the power alpha 2, del xn to the power alpha n. I can take the nth order partial derivatives. Those nth order partial derivatives must, in modulus sign, must be bounded, and it must remain bounded even when I multiply it by polynomial in several variables. Now I can multiply by polynomials in several variables. So the definition of the Schwarz space carries over in the most obvious manner to functions of several variables. So you can assume, again, to begin with, that our functions are in the Schwarz class, but Schwarz class of functions in several variables, x1, x2, xn. Then what is the Fourier transform of such a function? F hat of chi1, chi2, chi-n is integral over Rn e to the power minus I x dot chi. E to the power minus x, e to the power minus I x dot chi into f of x dx1, dx2, dxn. What is x dot chi? X dot chi obviously is x1 chi1 plus x2 chi2 plus dot 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 plus xn chi-n. The integral will make sense if the function f is in the Schwarz class. Exactly as in the one variable case, you can prove that if f is in the Schwarz class, f hat is also in the Schwarz class, and you can prove that f is a isomorphism from the Schwarz space to the Schwarz space. And you can also prove that the Fourier transform exchanges differentiation and multiplication. There, instead of 1 upon I ddt, now we have to look at 1 upon I del xi. That is one operator, and that's a momentum operator in the jth direction, and the position operator in the jth direction multiplication by xj. So the Fourier transform exchanges the position operator and the momentum operator component wise. So all those standard properties simply go through without any problem. The inversion theorem also goes through. The only difference is that in the inversion theorem, in the multidimensional Fourier transform, it's going to be 1 upon 2 pi to the power n will appear. The constant that appears in the inversion theorem is 1 upon 2 pi to the power n. And the Fourier transform of the Gaussian is another Gaussian. That theorem also goes through. Exactly with very little changes, because the Gaussian is e to the power minus a x1 squared plus x2 squared plus xn squared. Now that will factorize as e to the power minus a x1 squared into e to the power minus a x2 squared, e to the power minus a xn squared. If you try to compute the Fourier transform, you will end up computing the individual Fourier transform of these Gaussians, and you will take the product. So you should compute the Fourier transform of the Gaussian. So the Fourier transform of the Gaussian will be another Gaussian. So many of the things simply go through. The Hermet functions and the Hermet's differential equation has an analog in multidimensional theory. Instead of looking at minus d2 by dx squared plus x squared, you should be looking at minus the Laplacian plus mod x squared, where minus Laplacian is What is the Laplacian in n variables? It is del 2 by del x1 squared plus del 2 by del x2 squared plus dot 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 plus del 2 by del xn squared. The Hermet equation has its analog in several variables, and some of the problems that you're done with Hermet's equation in one variable will have its obvious multidimensional analog. So now we want to prove that the Fourier transform of a radial function, that is the function f depends only on the radius, the distance or the point from the origin, then the Fourier transform f hat of chi1, chi2, chi-n will also depend on the distance root chi1 squared plus chi2 squared plus dot 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 plus chi-n squared. Now the problem, the theorem is quite simple, and what we will do is we will prove this in the next lecture, and so I'll close this second lecture with this remark. Meanwhile, you should, before listening to the next lecture, you should try and solve this problem in say 2 dimensions and 3 dimensions. Do it in 3 dimensions and see what happens. If f is a function of 3 variables, x1, x2, xn, try to use spherical polar coordinates and try to solve this problem. As an initial hint, you have to first make a rotation of coordinates, and there is no harm in assuming that you can use a matrix and you can align this in the 0, 0, 1 direction. It will be a very nice exercise to do this in R3 or even in R2, doesn't matter, and see what exactly you get in these 2 cases. Reason why this kind of thing is important in physics is because many of the physical processes exhibit spherical symmetry or cylindrical symmetry. When you have a physical process involving cylindrical symmetry, you will see a 2-dimensional, the Fourier transform, radial Fourier transform appearing. In 3-dimensional problems involving cylindrical symmetry, you will come across the Fourier transform of a radial function in R3. I think we'll stop here for today's lecture. We'll continue this next time.